In this next video, we're going to look at differentials and linear approximations. And both of these two concepts go together very well. Both are related to using the fact that we know how to get the derivative of a function, but we're going to take it a little bit differently. So to talk about differentials, I want to start by looking at kind of this picture here. So I've got some general function f of x, and I've got the tangent line at a point a, which is in the domain of our function. Okay, so like a derivative, if I think about what the derivative here means, meaning the tangent line, or the derivative at a point, meaning the tangent line, it tells us what is happening to the rate of change of one variable, meaning the y, with respect to the other variable x. And as we saw with implicit differentiation, it doesn't matter what order I'm looking at. So I could say it's the change in x with respect to the change in y. Okay? What is different about a differential is that it is looking at the change directly proportional to the other variable. Okay? And I'll explain a little bit more what I mean by that. But looking at this picture, I want to point out a couple of things, because these are going to be useful for both the differentials that you're going to be asked to do, but also for the linear approximations. So here, if I look at a function and its tangent line at a point A, and I pick some point over here, which I'm going to call A plus delta x, meaning I'm taking some small distance, delta x, away from A, and I'm going to look at the points and just compare them. Okay? Well, if I look at the function value there, right, so if I continue my f of x off, I drew that kind of far over. Let me move it over just a little bit so that I can actually get it on my curve. Let's say there's our point on the curve. Then if I look at kind of the horizontal and the vertical distance there, I can label each of those in terms of what we've kind of shown here, right? This horizontal distance, that's our delta x, because it's the distance between A and A plus delta x. But also, if I look at the curve, this point on the curve is just going to be f of A plus delta x, which means the difference between the two of these is whatever the change in the function value is. I'm going to call it delta y. If you want, you can call it delta x, f, for function value. But if I'm looking on the curve, those are those differences. Okay? So if I'm looking over here, what this is saying is delta y is going to be f of A plus delta x minus f at A. Okay? Now that's something we learned back in pre-calc. Right? If I have two function values and I want the difference, I'm just going to subtract them. But what comes new is the fact that we're looking at that tangent line as well. Okay? So if I look in blue, I'm still going to use that same point A plus delta x, but instead of looking at the function value, I'm going to go up to the tangent line. So there's a point there on the tangent line that has the same distance away from A, but now when I look at those heights, notice the heights are very different. So if I look again at that vertical and horizontal distance, those aren't quite the same. The horizontal distance is the same. Okay? I'm going to call that horizontal distance dx. So it's not delta x anymore because I'm not on the function. But notice that your dx and your delta x will have the same length. Okay? Because they're both going to be delta x units from the point A. The only difference is one of them is on the tangent line. Okay? The point here, if I'm looking at those y values, so again, the point on the tangent line, the difference between this point, this vertical distance, is what we're going to call dy. Okay? And the first thing we should notice is that these are not the same. Okay? Delta x being small, okay, so if you remember our definition back when we talked about limits, delta x being small means I'm looking at something much less than 1, okay, on the order of like a tenth or a hundredth or something like that. And if it's small, that means this picture is kind of extremely blown up, but the relative change between the two of these is not going to be very big. And so we get two kind of things from this. The first is that dy, if we're going to calculate it kind of like we did our delta y, dy is on our tangent line, which means it's going to be the derivative at a plus delta x, so that point there, minus the derivative at a. And if we actually look at what this means, it's probably not clear or obvious at this moment, but if we actually look at what this means I'm looking at f prime of a times our delta x. Or, from what we said there, it's going to be f prime at a times dx. Okay? So there's our formula for our dy. Okay? And the other nice result we get, like we said, if we look at this kind of on the smaller scale, is that our dy is going to be approximately equal to our delta y. In some nice cases, those will come out to be the same. So for example, if I'm looking at a linear function, then the tangent line and the linear function are going to be exactly the same at the point, and so these would be equivalent. If my curve is approximately linear at a particular point, these should be very, very close. But as you can see, if my curve is actually curved, then my tangent line may differ, and so then these two values will be slightly apart. Depending on what your delta x is, these could be close or they could be very far away. Again, the bigger the delta x, the bigger the difference between the y and the delta y. Okay? So one of the things you're going to be asked to do is to use some of these formulas. In particular, you're going to need your delta y, so your change in your y values for your function. You're going to need your dy, which is the change in the y value from your tangent line. And you're going to need to know the two approximations, meaning the approximate value that dy is approximately equal to delta y, and that dx and delta x are exactly the same. Okay? Alright, so the first thing we're going to look at is just finding your differentials and finding some of your changes. Okay? So for example, let's say we had the function f of x equaling 2 square roots of x minus 1. And we want to let x equal 2 and delta x equal 0.1. Okay? Now again, in this case, my delta x is small. Again, I caution you because if you have a delta x that's 1 or 2 or something like that, where it's a nice whole number, your values may not come out so close. And so when you go to check, you've got to be aware of that. But for small delta x's, you should be able to approximate them and see that they are relatively close. Okay? So for this one, let's say we want to find dy and delta y at the values. Okay? So let's start with delta y. Okay? Delta y, again, is our change in function values. So in this case, the x that we're given, we're going to treat that like our a. That's the point we're starting with. And this is the point we're moving away from. Okay? So here, our delta y is going to be f of 2 plus 0.1 minus f of 2. Okay? And then we can plug in. So this is, again, going back to pre-calc a little bit, but that's okay. F of 2 plus 0.1, well, that's just 2.1. So we're looking at 2 square roots of 2.1 minus 1, minus our f of 2, which is going to be 2 square roots of 2 minus 1. Okay? Simplifying. Okay. And again, for some of these, you may need a calculator or something to calculate if they're not nice values. Some of them you might be able to evaluate nicely because you can change the decimal into a fraction easily. Some of the ones with square roots you may not be able to do that. So we'll go ahead and plug it in and just round off to some nice numbers there. So plugging in 2 times the square root of 1.1, we get 2.0976. Some more digits. Minus over here, well, square root of 1 is just 1, so that's just subtracting 2, which tells us our delta y is going to be 0.0976. Okay. For our dy, here again we're looking at the derivative. So we're going to take the derivative of our function and then plug in our values. Okay? The derivative times our dx. So this is our differential notation. And again, if you notice our differential notation, it looks a lot like your derivative. The only difference is there's no fraction here and the piece is over here. So if you want to think of this as dy dx, excuse me, equals f prime of a, you can do that and then move your dx over. That will work for almost all the differentials we're going to do. You have to be a little careful if you've got sums and differences, because you need to take into account that the dx will apply to everything on that side. So here, taking our derivative, we get a 2 times the square root, so 1/2 x minus 1 to the negative 1/2 times 1, so using our chain rule there. Again, we need to attach on the dx. Simplifying this and plugging in, so remember dx and delta x are the same, so our dy is going to look like 1 over our x, which is 2 minus 1 to the 1/2, times our 0.1. Okay? Nicely, when we look here, 2 minus 1 is 1, that raised to the 1/2 is still 1, so this is going to look like 0.1. Now again, like we said, if we look at our two values, our delta y was 0.09. If we round that up, that's about 0.1. And our delta y, or sorry, dy was 0.1. So these are relatively close together. Be careful where you're asked to round, especially in WebAssign. For some of your WebAssign problems, they will actually have you leave them as exact answers. So the ones that actually round to nice fractions or simplify down to nice fractions, you're going to be asked to leave them there. Some of them, they will ask you to round it to a certain number of decimal places. And you're going to have to be very careful. So I've seen students in the past who, for some of the approximations that we're going to do in a minute, they'll just plug it into the calculator and put that in, and they can't understand why they're getting it wrong. So keep in mind that these are similar, but they are not equal. Okay? So this is one example of what you're going to be asked to do with the differentials. So another look at your differentials, one of the other things you're going to be asked to do both in the homework and the WebAssign and on the exam is to just find the differential of a function. And so kind of like what we saw in the last example, it's basically taking the derivative. Again, the difference is when we say the differential, I'm looking at just the change in y, not necessarily with respect to anything. Whereas a derivative, it's a change with respect to something else. Okay? So for example, if I have y equals x plus 3 over 2x plus 1, and I want to find the differential, then I'm going to start it out the same way we did our derivatives. Again, my notation looks a little different. So because I'm looking at the differential, it's just going to be dy. So again, I'm thinking the change in the tangent line of y. We'll take our derivative. So in this case, we're going to need a quotient rule. So derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Okay, and again, the difference here is because I'm taking it here, the change in y is going to be directly proportional again to that change in x, so I need to attach on that dx. Okay. From there, it's just a matter of simplifying. So we'll get a 2x plus 1 minus 2x minus 6 over our 2x plus 1 squared. So dy will look like minus 5 over 2x plus 1 squared dx. Okay? And that's the differential. Again, in this case, since we're not given an x value and a delta x value, that's all we're going to do is just get the function for the differential. Okay? One of your uses for differentials is error analysis. And by error analysis, it just means if I've got some function that I'm evaluating at a point, but there's some margin of error in that evaluation. Okay? The best way I think of it is when me and my husband build reptile cages, and he goes to measure something and he says, oh, it's about 3 feet, and it's more like 2 feet 11 inches or 2 feet 11 and a half inches. He's got that margin of error in there. And so when we're talking about error analysis, we want to figure out if I know that margin of error on one unit, how does it relate to the margin of error on another? And so here's an example of that. Given the volume of a sphere being 64 cubic centimeters with an error of 0.2 centimeters, we want to find the error in the surface area. Okay? Now this is kind of a two-part problem. Some of the ones you're going to get are one part. Okay? And why I say this is a two-part problem is because surface area and volume aren't directly or explicitly related. They're kind of related through the fact that they both use the radius. But directly, there's no nice formula that you're automatically going to be given that says volume equals the surface area. Okay? It's usually in terms of your radius. So that's why this is a two-part problem. Okay? So given the volume of the sphere, so volume we know is 4/3 pi r cubed, and we know that this volume is going to be 64 cubic centimeters. Okay? They tell us the error in the volume, which that should be cubed. Okay? The error in the volume, meaning dV, is 0.2. Okay? So from this, just this 3 little pieces of information, we can figure out the error in the radius and the error in the surface area. Okay? And so what we would do is we start with our volume equation and we get the differential just like we did over there. So dV is going to equal, using our power rule, we'll get a 4 pi r, subtract 1 from the exponent, dr. So again, there's our differential of V, or the differential of the volume. And we know that 0.2 is 4 pi r squared dr. Okay. Now it almost looks like we don't have enough information to solve, but like I said, these 3 pieces together give us all that we need. And the only one we really haven't used is this one here. So we know that the volume is 64 cubic centimeters, which means that 4/3 pi r cubed has to equal 64. Okay, so we can solve for r. So we'll invert and multiply there. R cubed 48 over pi. So r is going to be the cubed root of 48 over pi. Okay, we can plug that into here and we can get our error in the radius. So I'm going to rewrite that as 2/10 4 pi times our cubed root of 48 over pi squared. And we can use that to solve for dr by just moving everything to the other side. So we'll take the 2 over 10. We're going to divide out by the 1 over 4 pi, or divide out by 4 pi, and then we can invert here, so pi over 48, that to the 2/3 is going to equal dr. Okay, now that's not pretty. We definitely want to clean that up where we can. Okay, so some things simplify. Okay. The pi to the 2/3 and the pi there gives us a 1/3 on the bottom. So dr so far is going to look like 20 pi to the 1/3 times 48 squared, all under 1. So there's our dr. units here. Again, always keep track of your units. In this case, we started with centimeters cubed for the volume, which means I'm cubing a centimeter. So there's our units on the change in the radius. Okay. Notice here it's not a rate. So with our derivative, it would be centimeters per minute or centimeters per something else. Here, because it's just the change in the one variable, the units are just the units. There's no rates for these. Okay. So now we can take that differential and again find the error in the surface area. So looking at our R, we know is the cubed root 48 over pi. Our dr, we know is 1 over 46,080 pi to the 1/3. Again, these are both in centimeters. Our surface area, well, we didn't put that formula up there, but that's 4 pi r squared. And so if we want the error in the surface area, again, that means I'm going to look at the differential. So again, take my derivative, attach on the one I'm taking it with respect to. So 8 pi r dr, and then it's just a matter of plugging in again. So our differential for the surface area is going to be 8 pi times the cubed root of 48 over pi times our 1 over 46080 pi to the 1/3. Okay. Now again, we can clean some things up. Some things will cancel out. Okay, so pi to the 1/3, pi to the 1/3, both in the denominator times that one there gives us a pi to the 1/3 in the top. We can take an 8 out of both the top and bottom here. Oops. Sorry, that one's on the bottom. And then the cubed root of 48. Okay, so there's our D of our surface area. Okay. Again, you could probably clean that up and get a decimal for it. So if this is your homework or WebAssign, they may ask you to round that to a nearest decimal place. That would be our simplified answer for now. But here we want to put our units on it. But there would be our error in the surface area. Okay. So one of your applications for your differential, again, is being able to use that to figure out some sort of error analysis. So the other use for our differentials is using linear approximations. The main use for a linear approximation is to get an approximation for a value of a function that is not nicely known. Okay, and so here in our picture, what we're looking at, this is that same picture we were looking at before. We're given some f, and here, if you like, you can call this df. That's our derivative at the particular point. So it's our tangent line. But if I'm looking here and I want to try and figure out this value, so this is the one we want. This might be a really nice known value. Okay, so I can take A, I can plug it into F, and I can get an exact value for it without problem. But in some cases, if I move just a little bit away from A, finding this value is not that easy. I really do have to go in and use like a calculator or some computer algebra system to figure that out. And the idea is, if I know the differential and I know the difference between my 2 points, then I can approximate that value by using the value at the tangent line. Okay? And so our linear approximation, and I'm going to use notation here. Some books differ on how they write out their linear approximations. They all basically say the same thing. A linear approximation at a particular point A. So let me write it correctly. The linear approximation at a plus delta x, meaning if I want to try and find this value here for my function, we can say that it is approximately f at a, so this point, plus our differential of y. Okay, now if you remember what we said our differential of y was, when we looked at our picture before, we said the differential of y, if we looked at that vertical and horizontal distance, it's that vertical difference between the point on the where the tangent and the function meet and the point on the tangent line at the new x value. Okay, so if we actually take that dy, as we saw before, makes this function be rewritten as the following. Okay? So there would be our linear approximation formula. I'm going to take the function value at the point I'm starting with, and then I'm going to add on the tangent line point times the dx, so that difference between it. That's our length dy. Okay. You're going to see your linear approximations written two ways, or given to you two different ways. So in some problems, you're going to be given the function, and you're going to be asked to find a linear approximation at some particular point. Okay. So for example, let's say that f of x is 3x squared minus 5x plus 2 over x. And we want x to equal, we'll go with 1, find the linear approximation. Okay. Now, if you are not given a delta x, like in this case here, then what we're looking at is just finding a function, meaning I really want to find L of x. Okay, so I'm going to find a function in terms of x. Okay, so again, first thing we're going to need is we're going to need our differential. So dy, again, is going to be f prime dx. So f prime times our dx. Again, this is an instance, don't forget those grouping symbols. Okay. So if I'm looking at my linear approximation, it's going to be f at 1 plus f prime at 1 times our delta x, or dx, which in this case we didn't get a value for, but remember, dx is just the distance between the two of these. Okay, so at some point over here minus our original point. And so in this case we can just say it's the x minus 1. It's the difference between those x values. Okay, so plugging in f of 1, well, if we plug in 1 we get a 3 minus 5 plus 2. Plus our derivative at 1, which looks like 6 minus 5 minus 2, times an x minus 1. Nicely, this first piece just goes to 0. If we're looking over here, it looks like a negative 1 times an x minus 1. So our linearization for this particular function at x equals 1 is going to be negative x plus 1. So this is one form of your linear approximations, and that's where you're given a function, you're given a particular x value, but you don't necessarily know dx. Okay? If I know dx, I can actually just plug it in here, and then I'm actually going to get a value. And so that's telling me what that particular point is approximately equal to, not just the function as a whole. So the other way you're going to see these is if you are given a particular function value to approximate. Okay? So in this case, if you notice, I'm not given an f of x, I'm not given an x, and I'm not given a dx. But I can find all of that information just by the piece that I'm given there. Some of these are going to be a little more obvious than others, so you may have to play around with it. So if I'm looking here, I want to approximate the square root of 3.9. Well, here that tells me my function has to be the square root, because I'm plugging some number into the square root function. Okay? Where this gets tricky is finding your x and your delta x. Okay? The way to remember this is your x should always be a function value that you know. So like I said, it should be one that you can easily calculate. Okay? If I'm looking at square roots, this is nice because only perfect squares are going to work. I want something close to 3.9 that's a perfect square. Okay? So here x is going to equal 4. Which means to find my delta x, I just need to figure out what the difference between these is. If my delta x, let me say it this way, if my value I'm looking for is less than my x value, then my delta x should be negative. If the value I'm looking for is bigger than my x, then my delta x is positive. Okay? So in this case, I'm looking at x equals 4. I want 3.9, so my delta x is going to be negative 0.1. Okay. Now that I have all of that information, I can find my linearization. So again, I'm going to start the same way by finding my dy. So dy, again, is my derivative times my dx. Okay. So dy will be 1 over 2 square roots of x dx. From there, I can set up my linearization. So again, L of x plus delta x is going to be approximately f at x plus f prime at x times my dx. Okay. If I'm looking here, L of x plus delta x, that is my square root of 3.9. It's always whatever it is you're trying to approximate. Okay, my f of x, well, you probably should use a different letter than x here, but my f at x is the square root of 4. My derivative at x is 1 over 2 square roots of 4. And my dx, again, is the same as my delta x. Okay, so my approximation is going to look like 2 plus a fourth. To keep my fractions nice, I'm just going to change this to a 1/10. Again, simplify where you can, so it looks like 2 minus 1/40. We can get a common denominator, so 80 minus 1 says that the square root of 3.9 is going to be approximately 79 over 40. And the best way you can check this is where you're going to want to check it with a calculator. For your homework and your exams, you're going to be asked to leave these as simplified fractions. Okay? And that's mostly just to make sure that you understand the process and that you can actually get the correct value there. In WebAssign, you may be asked for both. So some of your problems may ask you for the simplified fractions. Others will ask you to round it to a particular decimal place. In either case, your process is going to be the same. The last thing you'd want to do is just check and make sure that you're getting close numbers. And again, close is going to be relative depending on how small your delta x is. Okay? But there's your second use for your differentials, and that's the linear approximations. And again, you'll see it in both ways. You'll see some combinations of these where maybe you start out with a function and just the x value, and then later they ask you to evaluate it at a particular delta x.